Hello friends, you're welcome back to my channel. In this video, we're going to be looking at a series of practice problems under complex number. And this question I have on the board here says, evaluate the expressions and write your answers in the form of A plus BI. Alright, so it says to evaluate these expressions and write our answers in the form of A plus BI. First, I want you to understand that this is nothing but a complex number. And a complex number is nothing but a mathematical expression in the form of A plus BI, where A is the real part and BI is the imaginary part. So these are the questions and I. Alright, so let us start with the very first, which is I. So now, first I want you to understand that this one is nothing but multiplication under complex number. And whenever you are talking about multiplication under complex number, it is just the same way we expand common algebra. Alright? So we simply say that this times this, this times this, this times this, and this times this. So this particular term here, these two will multiply everything in this bracket, and this 5i will multiply everything in this bracket, such that we are going to have that 2 into 4 minus I, alright, then plus 5i into 4 minus I. So this is how to, so this now is trying to show that this 2 is multiplying everything here, and this 5 here is multiplying everything here. So expanding this bracket with 2, we have that 2 times 4 is nothing but 8, 2 times minus I is nothing but minus 2i. Again, 5i times 4 is nothing but plus 20i, yes, then 5i times minus I is nothing but minus 5i squared. Very, very important. Okay, so having obtained this now, I want you to know that in complex number, that I squared is nothing but minus 1. Alright, so please do well to check out my video under complex number. I dealt with all of these things. Okay, so now here, therefore, replacing I squared here with minus 1, I am going to have, and of course adding these two things, I'm going to have that this is minus 2i, this is 20i. So this is more like saying 20i minus 2i. I'm going to have plus 18i. Therefore, I'm going to have that 8 plus 18i plus 5. Because this is minus 5i squared. So if this I squared is replaced with minus 1, that minus 1 that will come out will multiply this minus 5 to give me plus 5. Therefore, I have this. Therefore, 8 plus 5 is nothing but 13. So finally, this expression is going to give, so I'm going to have 8 plus 5 plus 18i, which finally I'm going to have that 8 plus 8 plus 5 is nothing but 13. So I have 13 plus 18i, and that is my answer. Alright, so that's the answer for this particular one. So you can see how I solved it. So do well to take down the notes. So let's tackle the second one very quickly. Okay, for the second one I have, this is nothing but division of complex. Don't forget, the first one is multiplication of two complex numbers, and the second one is division of two complex numbers. Alright, so whenever I have a complex number like 1 plus 4i all over 3 plus 2i, right? Whenever I have a complex number like this, how I'm going to tackle this problem is nothing but multiplying the numerator and the denominator by the conjugate of the denominator. Therefore, the conjugate of this denominator is nothing but 3 minus 2i all over 3 minus 2i. Now, what is a conjugate of a complex number? A conjugate of a complex number is nothing but a complex number obtained by changing the sign of the imaginary parts. So, if you focus your attention on the denominator here, you find that this is a complex number whose imaginary part is positive. The imaginary part here is this 2i, and 2i is positive. So whenever, if I change the sign from plus to minus, the outcome will be the conjugate of this complex number. So now multiplying the whole of this complex number by the conjugate of this denominator has not changed anything here, because this is 3 minus 2i all over 3 minus 2i. So this 3 minus 2i these two things can still cancel out to still give you 1, of which when they multiply this is still this. So the reason why we have to multiply this and this, that is with the conjugate of this, is just to make the work a lot easier for us to evaluate. Or the another reason why again is to remove I from the denominator, because whenever you multiply a complex number by its conjugate, you think the outcome will no longer have the imaginary symbol I. Okay, so we are going to multiply the numerator the same way we tackle this one, and again multiply all the denominator the same way we tackle this one. Alright, so here now, this is going to let us, we can introduce a bracket like this. Now, such that 1 times 3 will give us 3, 1 times minus 2 will give us minus 2i, 4i times 3 gives us plus 12i, 4i times minus 2i gives us minus 8i squared. Now we are done with the numerator. Now down to the denominator, we have that 3 times 3 gives us 9, 3 times minus 2i gives us minus 6i, minus, now plus 2i times 3 gives us plus 6i, then plus 2i times minus 2i gives us minus 4i squared. Now notice on the denominator that this can cancel this. Very important. And again, don't forget that we say that I squared is equal to minus 1. So if that is true, it means that we are going to put minus 1 here and also put minus 1 here. And of course, if minus 1 enters here, we have plus 8. And if minus 1 enters here, we have plus 4. So if that is true, we are going to have now, and these two things can add up. So if we have plus 12i minus 2i, we have plus 10i. Therefore, we can say that we have 3 plus 10i plus 8. That's for the numerator. And for the denominator, we have 9 plus 4. Very, very important. Remember that the question says we should put this in the form of a plus bi. Okay, so now arranging further, we can add up these two to give us 11. So we have 11 plus 10i all over. Now 4 plus 9 plus 4 is nothing but 13. Alright, so notice that now in this case, now this is already in the form of a plus bi, but if you don't watch carefully, you might think it's not in the form of a plus bi. So evaluating this further, the final answer to this is nothing but 11 over 13 plus 10i all over 13. So this is in the form of a plus bi, such that 11 over 13 is the real part and 10i over 13 is the imaginary part. Okay, so that is it for question, or maybe the II part of this question 1. Okay, so let me quickly clean it and tackle the last one. So we move over to the next part of this series. Okay, so for the final one, which says exponential 2 plus I pi. Okay, let me just put it up here. Exponential 2 plus I pi. This is what we have. So we are asked to evaluate this complex number in the form of a plus bi. So how do we tackle this problem? First of all, we're going to apply the law of indices. Now, applying the law of indices, I want you to understand that this is equal to exponential 2 times exponential I pi. Because the law of indices states that whenever two things are multiplying themselves, or whenever two things that are multiplying themselves has the same base, you can take one of the base and add up the power. So this is now believed to be this according to the law of indices, because the base here is exponential and the base here is also exponential. So we take one of the base, adding the powers, we have something like this. So now arriving at this part, I want you to know that exponential 2, I mean to say, exponential 2 is nothing but a constant. Alright, so you can actually get the value of this. Now, and there is this form of complex number that says that the exponential form of a complex number z is nothing but r exponential I theta. So if you want to compare this now to this, you find that this and this can be compared. So comparing this, which is the exponential form of a complex number, with this, which we have here, you find that r is equal to exponential 2, and the whole of this exponential I theta is nothing but exponential I pi, where theta is pi, and of course, pi is nothing but 180 degrees. Alright, pi radians is 180 degrees, and this I is this I you see here. Alright, therefore, arranging this further, now this is something as this. Okay, so we can now say if this is equal to this, we also know another form of complex number, which is the polar form of a complex number that says that z is equal to r into cos theta plus I sine theta. So this is a form of a complex number called polar form of a complex number, and this is another form of a complex number called exponential form of a complex number. So this and this now are relatable, where r is this exponential 2 you see here, and this exponential I theta is this exponential I pi you see. Alright, now relating these two now, you find that this r is equal to this r. Now this cos and sine will always be there, and this theta and theta will always be the same, which in this case is this theta that is supposed to be here. So translating the whole of this now into this, you find that it is equal to exponential 2 into cos pi plus I sine pi. We have this. So at this point now, we can evaluate cos pi and also evaluate sine pi. So now, evaluating them now, you find that this sine pi is more like saying sine 180, and sine 180 is 0. And now cos 180 is minus 1. So this is now more like saying that this is equal to exponential 2 into minus 1 plus 0i. Alright, because sine 180 is 0, so put the I, and of course 0 times I is 0. So now expanding this further, you find that the whole of this is equal to exponential 2 plus 0i. Alright, so it therefore means that exponential 2 raised to power exponential 2 plus I pi is equal to this which you see. So this is more like saying exponential 2 only. So, but because the question has said put it in the form of a plus bi, the a part now is this exponential 2 you see, and this 0i is this bi you see here. Alright, so that is it for this first part of this series. So please, if you've not subscribed, commented, liked my videos, please do well to do that. And very much importantly, do well to like so that YouTube can recommend these videos to as many people as possible.